Thank you everybody for tuning in today to this talk by Jack Muir, who's finishing up his thesis at Caltech's, at ANU right now. He's a sixth-year student at Caltech's Seismic lab, and he's also going to be taking up a scholarship or a fellowship, as it's known, at Oxford, and he's going to be going there in late 2021. And he's really passionate about inverse problems, which is how I know Jack. We've had quite a few conversations at AGU over the last few years, and he's quite interested in seismic methods, as well as the mechanics and mathematics of inverse problems, which bring us these beautiful images that we all like to see. So today Jack's going to talk to us a little bit about compressive sensing and how that's applied to large sensor arrays, and in particular distributed acoustic sensing. But before we get on to the talk itself, we've got to do a little bit of housekeeping. These talks are made possible by the ASEG, and in particular our sponsors. Here's quite a few of our sponsors listed. There's down under geophysics, Santos, just to name a few. Here's our branch sponsors, and I know we're a little bit small in the ACT, but nevertheless, we are well represented by our technical prowess. Of course, if you have any questions, you can pop them into the chat. You can raise your hand. By this time, after 2 years in the pandemic, I think we're all experts in the use of Zoom, except for yours truly over here, because I had some trouble logging in, but nevertheless, I'm sure the rest of you are experts at being able to ask questions, and I'll be able to moderate them. Thank you, Alexa, for your help in setting this up at the Secretariat. And of course, here's why you should join the ASEG, because you get free access to Exploration Geophysics, which is a little bit of an applied journal, but it has a lot of very useful applied geophysics, near-surface geophysics research articles that you get access to. You also get preview, which you don't really have to be a member for, but I ask you to look it up. It's sort of like the equivalent of the SEG's leading edge, but with an Australian bent. So all the latest and greatest airborne electromagnetic or potential fields data releases that various state surveys or Geoscience Australia is collecting are released in that. There's minimal entry fees for students and members to AEGC conferences, such as the one being held in Brisbane in the next week or so. It's pretty unfortunate that we won't be able to meet in person, but we all know that our health comes first. In this time of the pandemic, I can't stress enough how important it is to keep your personal and your professional networks flourishing, and so being a part of the ASEG is quite helpful in that regard. And I think that's really all I have for now. So, if you want to keep in touch, there's all of these ways through social media, which I'm a complete klutz at. I don't know very much about. But all of these talks, including Jack's talk today, will be uploaded to the ASEG YouTube channel. And so I think it's quite a useful resource as a student or as a professional for you to be a member of the ASEG. So without further ado, Jack, if you want to share your screen, I will stop sharing mine. And
everybody see my
see your screen.
Great. Thanks, Anand, for the introduction and for pitching the ASEG. So actually, this ASEG talk for me has been something of a long time coming, because I was lucky enough to be supported by an ASEG student grant during my honours year back in 2014. And I believe a condition of the student grant is that you're supposed to give a talk at your local branch. And I managed to leave for America before I managed to fulfill that obligation of mine. So I'm glad that I can finally come back and hopefully give a broader and more well-researched talk, having spent some time as a graduate student than I would have been able to back in 2014, and to, in a small way, pay back some of what ASEG has given me. So I'm going to be talking today about preconditioned compressive sensing for Wavefield Reconstruction. And this is part of my thesis work at Caltech, so it makes up about half my thesis. At Caltech, people typically do two types of projects, and this one I did with Professor Zhongwen Jan, who is an assistant professor at Caltech, who's an observational seismologist, and in recent years he's really been focusing very heavily on distributed acoustic sensing. So a large part of this talk is going to be talking about distributed acoustic sensing and how this technique might be used for that. So without further ado, I'll launch into the talk. So the underlying motivation for this talk on Wavefield reconstruction is the idea that handling large and especially heterogeneous data volumes is going to be a major challenge of 21st century seismology. So over the last decade especially, we've seen this great proliferation and extremely dense acquisitions of seismic data. So at a continental scale, we've seen things like the famous US array, which rolled across the continental US in the early 2010s, and then it went up to Alaska after that, and it's just recently finished up in Alaska, which covered the entirety of the US with 70-kilometer spacing broadband seismic stations. We've seen similar sorts of efforts in other parts of the world, including the current efforts in Australia to also instrument in a rolling fashion the Australian continent. And we've also seen at a much smaller scale these amazing industry data sets. This one is a particular favorite of Caltech graduate students. This is the Long Beach Array in southern Los Angeles. So this area is an oil prospect site, and it was very, very densely instrumented in the early 2010s by Nodal Seismic company in LA. And you can see this is something like 5,000 geophones in the city of Long Beach, where you can see in this local earthquake crossing the Newport-Inglewood fault, actually, the action of the fault in scattering the wave field. You can see the different ways that the wave field progresses across the fault boundary, which is here in black. So there are these amazing new data sets coming out, which are very, very high density. And the reason why we want to have these high density seismic arrays is because fundamentally the seismic wave field is a 3D, or if you're lucky enough to have a vertical resolution as well, a 4D object. So that's in 3D, two spatial dimensions plus time, or potentially 3 spatial dimensions plus time. And therefore, in order to adequately sample the full seismic wave field, we've expended these major logistical efforts, which allow essentially quasi 3D measurements. So in this case, we have a quasi 3D measurement of the wave field. But when we're acquiring this data, the data representation is still often effectively in what I call an n by 1D representation. So that is, we have a bunch of time series, and we sort of lose to a certain extent the spatial characteristic of the data. Of course, we can plot them in a spatial way and recover it to a certain extent, but it's not a fundamentally space-aware representation of what the wave field is doing. And this is especially true for irregular or heterogeneous arrays. So irregular meaning that the spacing between the networks is not particularly regular, or heterogeneous meaning that there are different sensing modalities in the array. So not just accelerometers, but potentially strain meters as well, as I'll be talking about later in this talk. If we have access to the full wave field, we can do all sorts of things with seismology that we can't if we only have access to time series. So there's a whole world of gradient-based techniques, such as wavefield gradiometry or iconal or Helmholtz tomography, which enable us to really access the wave field in a robust fashion, access physical parameters in a robust fashion without having to perform formal inverse problems. So this is an amazing result from Derrida et al. In 2015 on the Ekofisk seismic array, which was in the North Sea. And they're seeing the phase velocity of Schulte waves crossing this array. And this is done totally passively with no calculation of Green's functions from ambient noise cross correlations or anything like that. They just recorded the passive noise on this array. And because they could differentiate the array in space, you can actually solve for the phase velocity directly from the wave equation. That's what's called wavefield gradiometry. But to be able to do this, you need to have access to correct gradients. And there's a world of spatial Fourier techniques, so beamforming and back projection, various migration methods, FK filtering, all of which are improved by dense sampling. This is another example of that, which I find really interesting. This is time frequency slowness analysis of scattered waves by one of the postdocs in Zhongwen's group, Zhenchen Yu, where he found this conversion from body to love waves within the inner borderland of Southern California. And this sort of work requires a dense spatial array to get the sort of K-space resolution that is required to see this scattering. And Of course, storage and compression are improved by recognizing the nature of the wavefield in 3D or 4D. We can take advantage of the redundancies that are inherent in a spatial representation of the data, then we might be able to compress it and store it more cheaply and operate it on it more efficiently. And so this, of course, links into the fact that these large end deployments are going to continue to be a major logistical and computational and financial challenge into the future. So we have these deployment trends of DAS, distributed acoustic sensing, which is thousands of channels recording at 100 hertz, which of course generates a vast quantity of data very, very quickly. So terabytes and terabytes of data are typically coming out of DAS deployments in the space of a few weeks deployment. We have dense 3-component nodal arrays started to go out in different locations. We have time variable deployment geometries. So a typical example of that, of course, are the rolling arrays that we have operating that are organized by governmental organizations like GA or USGS. And we have heterogeneous data sources that we need to be able to take it into account and to unify into a single product. And then in terms of computing trends, we have the concept that we want to operate more on time and space localized cubes of data rather than individual time series traces. So we want a time space localization rather than just time series. And also we're going to move increasingly to cloud computing, where they charge dollar per hour or dollar per compute unit rather than just buying a large computer, which means that we need to think about how we can operate on the data most efficiently, taking into account that we need to upload and download the data products and have some representation that makes best use of these cloud computing resources. So the concept of my talk today is how can algorithmic development move us towards capturing the full seismic wavefield in a way that sort of mitigates some of these upcoming challenges in large-scale seismic sensing. So part one is going to be talking about the Wavefield Reconstruction algorithm for point sensors and some of the applications that come out of point sensors. So the fundamental concept here is that seismic wave propagation depends on both the space and time derivatives of the wavefield fundamentally. So in this example of the elastic wave equation, we have two sets of derivatives. We have here on the left, MA. So we have the density times the acceleration, which is the second time derivative. And here we have the gradients of the stress tensor, which is a second order spatial derivative on the right-hand side. So second order in time and second order in space. And if we want to be able to represent the seismic wavefield accurately, that means we need to be able to calculate both second order in time derivatives and second order in space derivatives accurately. So seismic time series typically are sampled at high rates and relatively regularly. So this means the left-hand side of the equation we can get down pretty well. And that's essentially what the 20th century story of seismology was being able to make these records very, very accurate. However, on the right-hand side, what we have is that spatial data is typically sampled sparsely and irregularly. And this is especially true in research settings, which is what I'm more used to. Maybe in industry settings, people have access to higher density and more regular data, but certainly in research, it's very unusual to have dense regular spatial data. And this requires some kind of interpolation for spatial derivatives in order to be able to calculate accurately the right-hand side of this equation. And this interpolation needs to be able to work for irregular networks, because that's often what we have. When we do this interpolation, we want an interpolation that in some way respects wave physics, and this gives us better results. So this is an example from Zhongwen's 2018 compressive sensing paper, where he first developed this idea. And in this case, what he's done is he's taken these point sensors here in a synthetic experiment, propagated a wavefield and recorded it at these point sensors. And you can see you can't really see very well any kind of wavefield to the human eye on this panel here. But knowing that it's a wave field, you might think that using a plane wave basis might be a good way to represent this data. And so if you apply some of the techniques that I'm going to be talking about here, assuming a plane wave basis, you can get out this image of what the wave field looks like, which turns out to be very close to the true wave field. And so what you're essentially seeing here is an underlying assumption that you are expecting something that obeys wave physics, because plane waves obey wave physics. And by using that as your basis for interpolation, you can allow much more detail to be recovered than from traditional interpolation methods. So basically what this project has been doing has been taking this synthetic example that Zhongwen worked out back in 2018 and getting it to work on real data, which of course is a big challenge. Synthetics often work much more nicely than real data does. So we had to work on something that's more robust than what was in this paper and that could handle things that were present in the real world. So the algorithm has essentially three aspects. The first is the fairly obvious one that's probably true to all seismic workflows, which is data quality control. And that's because anything that interpolates in space is going to be affected by bad data quite strongly, because often in space we don't have very many records. And so we need to do data quality control to remove any bad traces. We then take each individual time series, so here's a time series seismogram, and we transform it into the wavelet domain, which is a time frequency representation here. So here we have in time, same time as the waveform. And here we have the frequency content. Here it's in period because it's a long period waveform. So we have high frequency at the bottom and low frequency at the top. That represents the waveform in this 2D representation here. And the reason for that is that seismic signals are strongly non-stationary in their power content in both time and frequency. And that means that we need to do different kinds of regularization when we go to the next step, which is to use compressive sensing to obtain a sparse curvelet representation for each individual wavelet in this representation. Curvelets, I'll talk about, an excellent basis for representing propagating wavefields, and in fact designed for that purpose. So to go into the second two steps in slightly more detail, the reason why we perform the wavelet transform is essentially to allow time frequency dependent regularization of the curvelet step. Wavelet power, which is represented here, is heterogeneous in both space and time. So if you take any slice through the y-axis or through the x-axis, you can see that it's not constant along either one of those slices. And so what we need to do when we are trying to determine how best to perform some kind of spatial interpolation is that we need to balance the strength of the regularization of that interpolation conditioned on each individual power in this representation. And so by splitting it up into this time frequency method, we can optimize the curvelet representation that I'll talk about next at each time and period. The curvelet representation is a way of sparsely representing packets of wave energy. Curvelets look something like this. They have angular resolution, they're spatially compact, and they have scale. So you can see it sort of looks like a plane wave that's been tapered. It has a particular angle, and it has this particular scaling where it's longer parallel to the wavefronts than it is perpendicular to the wavefronts. And these objects were designed in the early 2000s essentially for wave physics problems that they're designed to optimally represent packets of propagating wave energy. And in order to represent the wave field in this basis, we do something known as compressive sensing, which is essentially trying to find a sparse collection of these curvelet coefficients that best represents the data. And we do this by solving an inverse problem that looks like this. So we take the argmin in respect to this model parameter M, which is the collection of curvelet coefficients of this G times P is a data, is like a forward modeling, a linear forward model matrix, fitting it to the data under the L2 metric. And then we add some regularization lambda here with the L1 metric here. And this lambda is the thing that is scaled for each individual one of these pixels. And that's why we need to create this representation so that we have an individual lambda for every time frequency combination in the time domain. Sparse solutions reduce the overfitting and promote robust reconstruction of the image. And it's due to this sparsity that we can get great results like this, where only a few plane wave coefficients represent this quite complicated looking wave field. In particular, the curvelets have this parabolic scaling relationship where the scale at a particular curvelet level J goes like 2 to the minus J perpendicular to the wave field and 2 to the minus J over 2 parallel to the wave field. And so if you look at this, you can see that if we were to penalize the scale with a preconditioning matrix that looks like 2 to the minus 2J, you're essentially penalizing the second derivative of the wave field. So by adding this preconditioning term, we're saying that we expect that the wave field should be relatively smooth, and that enables us to be able to robustly calculate the second order spatial derivatives rather than just the 0th order spatial representation of the wave field, which is really important for being able to get out the spatial techniques that I talked about earlier in the introduction. Why does the L1 metric promote sparsity? Just as a side, for people who aren't familiar with compressive sensing, if we think about normal L2 type regularization, which would be having a 2 here. So this is the sum of the absolute values of the vector m. The L2 would be the square root of the sum of the squares of m. What it looks like basically is that is a circle in high dimensional space, or a sphere in high dimensional space, and then the data fitting here is some kind of hyperellipse. And so what you're looking for is the minimum of the sum of these two objects. And if you have the L2 norm, basically the minimum is going to be anywhere in your high dimensional space. But if you have L1, it looks like a hyperdiamond. And when you get very high dimensional hyperdiamonds, it turns out that you're very likely to be near a corner of the hyperdiamond. And so that essentially means that a lot of the coefficients are going to be 0, and that promotes sparsity. So that's why the L1 metric promotes sparsity in these compressive sensing problems. And when we have sparsity, we have more robust imaging, enabling us to get this good interpolation. So I'll go through some pretty picture examples. So this is the 2019 Ridgecrest magnitude 7.1 earthquake. It has a complicated wave field with high curvature and scattering, and this is recorded on the accelerometer stations in Southern California. This is 100 seconds after the origin time of the earthquake, and we can see the energy propagating across the Southern California region. If we just do linear interpolation of the wave field, we can see something that looks like a propagating phase front. It's quite confusing out here. And then if we take the second order spatial derivative, it basically looks like complete junk. We can't get any useful information out of this Laplacian. It's non-physical. If we do something slightly more sophisticated, like curvature minimizing spline interpolation that's been used for Wavefield reconstruction in the past, we do get a maybe nicer result for the straightforward spatial interpolation, but when we get to the Laplacian, again, it doesn't look very good and it's not useful. If we use our algorithm, both the velocity and the velocity Laplacians look more physical. There might be some artifacts here, but overall, we actually have a physical Laplacian, especially along the main wave front that we're interested in. And so we're able to get a much better representation of the wave field, including, crucially, the second spatial derivatives that I've been talking about using our methodology. Despite the relatively strong regularization that is induced by our method, we do actually fit the data very well. So we're not underfitting the real data. We are representing the wave field correctly in time as well as in space. So that's one example using real data. What can we do with this sort of representation? Well, as I said before, Wavefield reconstruction allows the use of these whole wavefield tomographic techniques that were previously only accessible for extremely dense industry level arrays. So for instance, this is a Wavefield reconstruction of the November 19 magnitude 7.0 loyalty. This is in 2017, I believe, or 2016, sorry, I forgot the year, Loyalty Islands earthquake crossing Southern California. And we can see if we take this data, we do the reconstruction, and we can get a Laplacian that looks very good. We can fit both the time domain waveforms, and interestingly, if we filter them, say at 30 seconds, we can calculate the acceleration at these two test stations, USC and VTV, and we can also calculate the spatial Laplacian and then multiply it by the best fitting phase velocity squared. So this is essentially assuming that the wave field obeys the acoustic wave equation, which is true for surface waves propagating, or single mode surface waves propagating across the array, which is what this is. This is the Rayleigh wave propagating across Southern California. And they fit extremely well. So the method is actually working quite nicely. And this means that we can actually just read off the phase velocity directly from this waveform. There's no inversion to be done, and it produces quite a reasonable looking phase velocity curve. And it's amazing that we can do this with only a single earthquake, that we can actually produce results that look comparable to inversions that require many, many hundreds of earthquakes and a large amount of computational resources to achieve. If we do this at all these stations, we can actually create a phase velocity map that looks quite similar to comparable phase velocity maps for the region. And again, this is using only a single earthquake. So we really make the best use of the available data using this sort of methodology. Some more exotic and interesting things that we can do with this methodology include things like Helmholtz-Hodge decomposition. So this is basically taking the wave field recorded here. This is the community seismic network in Los Angeles, which is basically a bunch of accelerometers in high schools in the Los Angeles area. This is the Ridgecrest earthquake again, and it's a mixture of different phases. And we want to be able to separate out those phases. And if we were in a relatively uniform area, you could do that pretty easily just by taking the transverse components and the radial components and separating them out, because we expect that the PSV and SH systems are well separated, but here we have the edge of a basin, and so we have this curvature of the energy as it crosses the basin, which means that it's not very easy to do that. So what we can actually do is set up an inverse problem to decompose the wave field into irrotational and solenoidal components. This means something that has no curl, and this is something that has no divergence. And this corresponds to the PSV system, and this corresponds to the SH system of the propagating wave field. And so what you actually get out of this is a separation into Rayleigh and love wave components of this surface wave train, despite the fact that there's a really steep basin edge across the array. We can see here that the strongest phase is clearly irrotational, which corresponds to a powerful love wave that was greatly amplified as it entered the basin. And actually that formed a large part of my other PhD work, which I won't be talking about today. But this enables us essentially to decompose this wave field here in blue into these pink and gray components that correspond to the two different systems of separated energy. So for the second half of the talk, I'm going to be talking about distributed acoustic sensing, or DAS, which is a new technique that is a large part of the group that I'm in Caltech. So distributed acoustic sensing is a new modality allowing fiber optic cable to be turned into thousands of seismometers. Essentially how it works is that people send a laser pulse down the optical fiber, and because the optical fiber has imperfections, it's constantly backscattering light. If we look at the backscattered light and then measure phase changes in the backscatter, the gradient of those phase changes essentially corresponds to the strain on the cable. And so if you measure those phase changes in time, you get a time representation of strain. And in order to determine where along the cable you are, you just do time of flight, because the index of refraction of the optical fiber is known. You can just multiply the index of refraction by, or the inverse index of refraction by the time to get the distance along the cable that we are looking at with the backscattered light. So this basically enables the optical fiber to be turned into as many stations as we have computational resources for, and depending on the pulse rate of the laser, gives us a maximum distance along the cable that we can look at. But it's an amazing technology, essentially, that enables many, many thousands of instruments to be created in a relatively fast fashion, because you can just plug in these interrogator unit boxes into an optical fiber and then now have this instant seismic array. But it does offer specific challenges for wavelet representation. So specifically, the channel spacing is very dense in 1D, but irregular and sparse in the other dimensions. We have access to the strain rather than the displacements, which is sort of a strange quantity to look at, which complicates theory and practice of sensing. And often the way the community has worked is that in research, at least, we're often working with what's called dark fiber, which is to say that researchers don't put the fiber into the ground. They just take the fiber that somebody else is not using and put their boxes on it. And so it's not necessarily designed for array performance. So we see some typical examples of deployment here from one of Jorman's review papers. This is the Porotomo experiment in Brady, Nevada, that I'll be talking about some more. This experiment was specifically designed to compare point sensors, which are the crosses, and DAS, which is the blue line. And so we see a relatively dense DAS deployment and a dense nodal deployment. So this is sort of not necessarily optimal, but a good sort of DAS array. But some other examples include, this is the Stanford DAS array, if I remember correctly. So this is basically a typical city-style array where you have a bunch of fiber optic cables going between buildings, and you end up having this sort of very square-shaped distribution of fiber. Or even more likely, we have things like this. Oh, sorry. This is the Fossa experiment, where it's just a linear piece of fiber in the ground. And so we have very good density along the fiber, but nothing off-axis. And here we have the Goldstone array, which is a loop of fiber that goes around different satellites, dishes. This is the equivalent of the Tidman-Biller Deep Space Network. It's another one of the Deep Space Network installations. This one's in the desert of California. So how do we do our wavefield construction with distributed acoustic sensing, and how do we combine it with point sensors? Because as I said, one of the challenges going into the future is going to be combining heterogeneous data sets. So the idea here is, once again, we're going to start with the wave field as a 3D object as the fundamental object of interest, rather than just individual time series. We're going to optimize the wave field to fit both DAS and nodes simultaneously using compressive sensing, or potentially DAS or nodes by themselves. And we're going to look at how we can optimize the geometry of the deployment to promote compressive sensing solutions. So in the DAS form, we go through the same processes. So essentially we pre-process and then wavelet transform the records. So we end up with a wavelet transform of the data. So starting with the time domain records for some channel type I, we pre-process them, do the discrete wavelet transform, and then we end up with this wavelet transform of type I. And then we construct the velocity matrix. We construct the velocity G matrix. So what the curvelets would be seeing in velocity space rather than strain space from the interpolation of curvelets at the locations of the different stations. So this G here is the overall sensing matrix, which is constructed by some interpolation weights, the curvelets themselves, and the preconditioning matrix that I talked about earlier. And then for DAS, it turns out that essentially what DAS is sensing, which we'll call epsilon C, is the projection of the strain tensor onto a particular direction and then averaged over what's known as a gauge length of length L, which is typically about 10 meters. And so the measured DAS strain is given by 1 over L, the integral of this epsilon C along the cable length L. And so what we can do is basically just calculate this epsilon C for the different DAS components and then integrate it in order to give the correct DAS forward model matrix. So this is shown here for the X velocity components. We differentiate the G matrix in respect to X, multiply it by these sine terms or sine 2 terms, and then integrate it. Likewise, for the Y components, we do the same thing. So this splits up into 2 different sections because of the way the strain tensor works. And then we're solving this sort of inverse problem where we have 2 curvelet coefficients, one for the X components of velocity, one for the Y components of velocity, fitting the wavelet coefficients of the DAS. So it forms a sort of linear system like this. And then it becomes very simple to incorporate point sensors here, because we have a linear system for DAS, and we also have a linear system for the X and Y components of the nodes, which will be the point sensors. So if we want to, we can form just a big linear system like this in order to incorporate all of the data sources together. And what that gives us is the curvelet coefficients for X and for Y, which we can then just go back up the steps of the algorithm in order to get the time domain records of X or Y at any arbitrary point in the domain. So what we get from this is a representation of the X and Y components of the wave field for a heterogeneous set of data. So in the real data experiments, we're going to be using the Brady NV Porotomo Experiment, which is an open access data set supplied by UW-Madison. It's probably the best opportunity to do this to date because we have a 2D DAS cable as well as a 2D. So what I mean is that it fills a 2D area, and we have a dense nodal array in the same location. And there was a useful magnitude 4.3 event nearby that can be used to analyze the cable performance. So the first thing to do is to just doing the normal algorithm, looking at the nodes, see if we can synthesize the DAS records. And this we can do very well. We match the phases extremely well, and we generally match the amplitude of the DAS records at all sorts of locations on the cable. And this sort of operation is useful because it enables us to calculate how well the cable is performing. So DAS as a new technique is not really as well calibrated as the nodal data. And so this acts as a way of calibrating the nodal data in a way that incorporates all of the cable and all of the nodes simultaneously, which is useful because normally you need very precisely co-located nodes and DAS cable to do this calibration. So they couldn't actually calibrate the entirety of the DAS cable at once, or they couldn't calibrate the entirety of the DAS cable because the nodal geometry wasn't necessarily optimal, but we can do that using our technique, as I'll talk about in a second. We can also synthesize the nodal records directly from the DAS. So this is just doing Wavefield reconstruction on the DAS by itself, and then trying to synthesize what the velocities of the nodes should be. And in this case, we typically match the phases okay. In the P wave, which is at the very beginning of the records, we can match both the amplitudes and the phases quite well, actually. In the S waves, we can match the phases okay, and the amplitudes are more difficult to match. And that's probably due to some kind of difficulty in modeling the ground coupling of the DAS cable effectively, and also because the DAS is only recording the derivatives of the displacement field. So we're essentially trying to do an integration here with noisy point measurements. And that's quite a challenging thing to achieve. If we look at the statistics of the misfit of this particular plot, averaged over all of the different DAS stations, that's about 7,000 stations, we get some interesting effects. So just looking at the blue curves for now, we can see that we have typically well-matching cross-correlation values of what the synthesized DAS records are compared to the true DAS records. So we're typically getting the correct wave fields for most of the array, but we have relatively significant amplitude errors. And so the idea here is that we can actually correct for the ground coupling of the DAS array using the nodal array and Wavefield reconstruction. We can also combine the DAS with nodes, and this substantially improves the reconstruction performance, especially at lower array densities. So this plot is basically a five-fold cross-validation experiment with different numbers of nodes. The blue curves are when we use nodes only and then try to predict what the wave field should be at left-out nodes. So in each case, we took 20% of the nodes out as a testing or validation data set, and from the remaining 80%, we then split that also into 5 sets. And then we started with only 1/5 of that remaining 80%, then 2/5, 3/5, 4/5, and all of the 80%. So this is 80% of the nodal data predicting the left out 20%. And then we compare that with doing the same thing, but adding the DAS. And other than this rather strange curve, which is doing something weird, we see generally at low nodal densities, adding the DAS really improves the ability to predict the wave field at the left out data set, at the left out nodal data. At higher densities, it saturates, and that's again probably because of the ground coupling. So the DAS isn't necessarily recording the true wave field. So coming back to that, what we want to do is to correct somehow the DAS data using the wave field reconstructed at the nodal data. And that's what we've looked at here. So this is the RMS amplitude ratio between the predicted and observed DAS, and it shows spatially coherent misfits. So we see basically the largest effects are in the southwest and northeast in this direction of the array. So this section here, this section here. This is true across both the P and S phases, throughout the period range studied here. And if we take the median of all these plots, we can see here that it's basically the same as in each individual plot. So it's a consistent effect that is causing misfits here and here. And if we look at the geology, we can see that it's actually in this quaternary alluvial section here and here that the misfits are greatest. So it seems like there's some kind of geologic control on the DAS misfits. So can we use this to then correct for the DAS to make it a better sensor? We can do this in two sort of ways. We can do it in a naive way, which is essentially saying we're just going to gain correct by this RMS amplitude misfit. And that's what's given by the green curve here. So that's a naive amplitude correction. You can see it substantially improves the RMS error of the amplitude here, but it can't change the waveforms at all because we're just multiplying it by a single number. We can do more advanced methods, which I'm not going to be talking about today because we don't really have time, using homogenization theory. And that enables us to both better fit the amplitude and also improve the cross correlation value, so the waveform fit in terms of the phase match, if we do this more advanced methodology. But in both cases, what we've shown is that we can use this co-located nodal array to substantially improve the performance of the DAS array by supplying corrections for what the amplitude should be doing and the phase should be doing in an empirical fashion. And then just briefly, finally, the last thing that I wanted to talk about is that we can also use these Wavefield reconstruction and compressive sensing ideas to do design of mixed DAS and nodal networks. So this is something that I think is going to be really typical in the future, which is that we often have a cable location that's out of our control. It's going to be something that we plug a box into, and it might be in an urban setting where we have something following the grid of the city or something like that. And the only thing we might be able to control is we might be able to put out some other sensors, so geophones, nodal sensors, something like that. And we have more control about that, where we will be able to put those. And so how can we do some kind of design problem to mix these two data sets together in an optimal fashion? And it turns out actually that this is a simple linear optimal design problem under the compressive sensing theory. And so you can set up basically a problem like this, where we have these two matrices that are just linear combinations of the rows of the big G matrix that I talked about earlier. And you can use this to select the nodes by trying to minimize this function. And this is something that has really well-developed theory for 50 plus years in the optimal design world. And if we do this for this particular synthetic test network that I was playing around with, we can actually see that if we look at the random unweighted, which is basically saying we will randomly select some of these red stations to include in our network, between 4 and 64 of them, or we will try to do some kind of design, either using what's known as the random weighted methods. That's basically using probabilistic weights determined from this optimal design problem. Basically solving this equation is actually quite challenging. It's a mixed nonlinear integer programming problem. So you can either try to solve it by relaxing it into a non-integer problem and then rounding it in some fashion, or by interpreting the relaxed weights as probabilistic weights. And that's what the orange curves are doing, is interpreting them as probabilistic weights. Or we can do it sequentially, which is to say we will take one station, solve for the best solution of this equation and put that station in, and then fix that station, move to the next station, add that in somewhere, and so on and so forth. And we can see that if we do that both using the probabilistic interpretation and using the sequential insertion method, we can get substantially improved misfits compared to just randomly selecting stations. So we can actually do optimal design for these mixed networks in order to improve our ability to understand the wave field. So that's the end of my talk, but some key takeaways that I want people to remember is that what we've talked about here is a new algorithm for wavefield reconstruction using a classical machine learning technique, which is compressive sensing, which enables us to robustly fit the waveform. The key finding here is that non-stationarity of seismic signals means that we need multi-scale regularization with an appropriate preconditioning to penalize the spatial Laplacian correctly. And we are moving towards essentially a more physical and intuitive presentation of seismic data, which enables multiple new wavefield techniques. I've got some videos of the Helmholtz-Hodge decomposition at this QR code. If people would like to follow me on Twitter, I'm happy to continue to present my research in that sphere as well, and to meet up with anybody in that social media space as well. So once again, I'd like to thank Anand, GA, and ASEG for inviting me, and I'm happy to take any questions that people have.
Thank you for that, Jack. That was quite an illuminating whirlwind tour of compressive sensing, L1 norms, and DES, and potentially how useful these technologies are. So if you want to ask Jack any questions, and I highly encourage that you do, please type them into the chat or raise your hand, and I'll be able to take it from there, and I can unmute the necessary participants. So I'm just looking to see if there aren't any messages. So are there any questions yet? Okay, I see Malcolm has a question. So Malcolm, I'll just allow you to talk. How about that? So Malcolm, if you unmute yourself.
Hello, can you hear me?
Yes.
Great. Jack, great talk. Really enjoyed it. I just wanted to ask about probably about the first part of your talk. Two aspects that you mentioned. One was noisy data had to be thrown out because of the amplification effect in noise propagating into derivatives, I assume. How sensitive is the sort of wavefield reconstruction to those noisy seismograms, and how, what's the guideline? That would be my first question. How would you throw that? How would you know what to throw out and what not to throw out? I guess that's my question. And the second one was more of a technical one of you're essentially using Lasso CV there, or I think it's all Lasso, yeah, Lasso CV to get the coefficient and impose sparsity on those systems. So I just wanted to ask about the performance of that in terms of the size and the stability, the size of problems you're able to solve, and how stable such things are.
Sure. So in regards to the first question, what we've found is that obviously you have a somewhat robust solution because the L1 metric avoids overfitting more than the L2 metric does. But if you have extreme data outliers, that can still be an issue. And so what we've basically done, I think, is probably what is a sensible method in any seismic data processing, which is to basically look for things that don't have good correlations with the rest of the wave field. So if they're very incoherent with the rest of the wave field, or if they have very different amplitudes to the rest of the wave field, then we've removed them. And that really is more taking out things that have had technical problems with the channel. So if there's like if the channel is actually just recording like electronic noise because it's decoupled, a cable's come loose or something like that, if you keep that in the inversion, that can really bias it, but it really should be thrown out anyway because it's not real data. Anything that could be construed as quote unquote real data, even if it's a bit weird, isn't probably going to be kept by most of the pre-processing methods that I used in these examples. In terms of the Lasso CV, so the cross-validation gives what I would call the gold standard of performance, I guess, because it really does test a lot of things very thoroughly, and that's for choosing the regularization parameter. But it turns out that if you use the corrected Akiyiki information criterion, which is much cheaper to compute, then it gives almost identical results in most of the examples that I showed. And so I actually use those for the larger problems. And we expect that to be more correct for large problems, actually. So that enables us to scale up to quite large systems. And so for the DAS examples, we have order 8,000 channels and several tens of thousands of curvelet coefficients. So it's a relatively, mid-sized, I'd say, linear system that you're solving. But it's difficult to solve, for people who aren't aware, it's difficult to solve L1 problems compared to L2 problems because it doesn't have a closed form analytical solution like the L2 norm does.
Yeah. Can I put an add-on to that? Have I still got the talking stick?
Sure, Malcolm.
Yeah. So you made me think of something there. So how necessary is it to use an L2 norm on the data and an L1 norm on the model? Could you use an L1 norm on both? And if you do that, it opens up different classes of techniques to solve the system because it's all L1. So there are sort of reweighted least squares. Even the old 1980s related least squares will solve an L1. Well, will tend to solve an L1 system. So I just wondered about that.
And if I could just add to that question, Jack, I was going to ask about the fact that, yes, if you're solving an L1 in the data, well, that should also not be sensitive to outliers, right?
Right. Yeah.
Yeah. So I think it's definitely something that could be worth thinking about. I'm not sure exactly how the sparsity is affected by having two L1 norms. It's not something, to be honest, that I investigated because I was trying to keep this as using as much like vanilla solving packages as possible. So things that were very openly accessible, and almost all of those are really predicated on solving this form of the problem. That's another reason why I introduced the Laplacian as a preconditioning matrix rather than adding extra like Tikhonov regularization on the Laplacian, say, which would be an alternative way of trying to impose those sorts of constraints. So what I really wanted was to formulate the system in such a way that it could plug into machine learning stacks. And the reason for that is just because they have high performance, because they've been really optimized to the nth degree to solve big systems. So it's definitely worth considering. I actually have no idea how the sparsity would operate under the heuristic that I have of a hyperellipse and a hyperdiamond intersecting with each other doesn't work as well when they're two hyperdiamonds. I'm not sure exactly what would happen. So no, good. I just wondered. That's good. No, great talk. Thank you.
Thanks, Malcolm, and thanks, Jack, for that. For being able to think on the spot about not a very obvious, question like what would happen if you had two L1 norms in your objective function. Any other questions? I see Dmitry Shagalov. I will allow you to talk as well. And if you could unmute yourself, that'd be great. Dmitry? We can't hear you because you're muted, so you're allowed to talk, but maybe I can unmute you. So no, I can't unmute you. You'll have to do it yourself. Dmitry, can you, do you want to say something? Because no, maybe you should look for your unmute button. In the meanwhile, we'll go to another question if there is one. Does anyone else have a question? No, Dimitri is also stopped asking his question. Well, in which case, I'll ask you a question, Jack. So when you were talking about industry data sets and how finely sampled they are, well, we were trying to solve this full waveform elastic reflection seismic problem, which is pretty difficult. And so one of the we tried to do it simply. We went to an area which was predominantly 1D. This was in the North Sea. It was fairly layered geometry. It's around the Alba field. I think there's a bunch of open source ocean bottom cable data available as well if you want to look at it. And what we wanted to do was compute the full wave field and solve the full nonlinear inverse problem and get full nonlinear uncertainties as well. And as you know, one of the hard parts in that task is to do the forward modeling such that you've got to solve the Sommerfeld integral. So you've got to do these Hankel transforms, which are really expensive, and they've got all these singularities. And if you don't have a little bit of attenuation somewhere, they're very difficult to solve. So what we initially thought was, instead of going from frequency and wave number to time and offset through a Fourier transform and a Hankel transform, we thought, well, why don't we do it the other way around? Why don't we do a wave number transform on the data and do a Fourier transform on the time series, and then so you get into the FK domain in your data, and you don't have to solve the Hankel transform in your modeling. But what we found was that we were severely and very badly aliased, and we weren't able to ultimately do anything by transforming the data, because despite the fact that the ocean bottom cable is pretty densely sampled, we were just not able to transform the data appropriately into the wave number space. Do you think your methods could help?
So were you just trying to do it in like a 2D inversion, or were you trying to do a 3D inversion?
So the Earth model was 1D, but the physics was 3D. Yes. The
physics was 3D. So you have, I guess, in that case, you have this sort of situation where you potentially have like good, K-space resolution in some directions and poor in other directions, because of the cable geometry, I'm assuming.
Yes.
Yeah, so it might be able to help. I think that the difficulty is always that, as I suggested, the pure cable by itself, it's often difficult to get a really high performance, because it has this anisotropic K-space resolution, basically, because you have very dense sampling in one direction and not so good in the other. But it does seem to improve it over just trying to do some kind of direct inversion. I guess in this particular case with the cable, it's is it like geophones on the cable, or is it a strain?
It was actually hydrophones, right? So
hydrophones on the cable, yeah. Okay, yeah, no, it'd be interesting to try how that would work. Especially with hydrophones, it might work quite well, actually, because then you don't have this added complexity of only measuring the gradients of the wave field, which is the difficulty with DAS, is that you're trying to integrate from the gradients up to a displacement representation. But if you're just measuring the displacement directly, then it's easier to estimate the curvelet coefficients, definitely. So it might be able to work quite nicely, actually.
Huh. So yeah, maybe that's something we could look up in the future. Are there any other questions? I don't see any other questions. So in which case, well, thank you very much, Jack, and all the best in everything you're doing, including wrapping up your thesis. And hopefully, with some luck, you're able to be off by the end of this year. Is it?
Probably early next year now.
Yes, it does seem a little bit like that. But again, thank you very much for your time. Thank you for a wonderful presentation. Thank you, everybody, for your time and listening to Jack and participating in this. And until our next meeting. So thank you very much, and bye all.
Thank you all. Bye.